This lecture is going to consider radiation from an arbitrary source. And it's actually going to be kind of an involved derivation, so it's probably going to span about 3 or 4 video lectures. So this kind of now generalizes our previous derivations where we derive the radiation from a dipole, electric dipole, and radiation from a magnetic dipole. In this case, what we do is we're going to consider some source, which is this blob right here, and we want to see what is the radiation that you would get if you have some little volume of charge right here and some currents that are flowing inside this volume. So what we're going to do is now label all of our distances. So the distance from the origin to the charge, we'll use our familiar r prime. The distance to the point in space where we're measuring the fields is going to be r, and the distance between the charge and the point in space is going to be script r, like we normally set up. Okay, so if we write down now the electric potential, which is now time dependent, we're just going to use our generalized form of a charge distribution at some location r prime at some retarded time divided by the distance integrated over the volume. Okay, where we can use the law of cosines to say that script r is the square root of r squared plus r prime squared minus 2 r dot r prime. Okay, so what I'd like to do is apply an approximation. So our first approximation says that the distance that we're measuring is much, much bigger than the distance from the origin to the charge. So r is going to be very far away from the source. Okay, so now if we use the binomial, so that reduces it to r squared minus 2r dot r prime. And if we use the binomial expansion, then what we get is a factor out in r, and what I get is 1 minus 2 r dot r prime over r squared. Well, I'm sorry. I'll factor out the r first, and then I still have to take the square root. Now I'll apply the binomial expansion and get r1 minus, so the 1/2 cancels with the 2, and I get r dot r prime over r squared. Okay. And now I can do the same thing for 1 over r, and what you find is you get 1 over r, 1 plus r dot r prime over r squared. So we had seen that before in previous lectures, doing the binomial expansion on r and the binomial expansion of 1 over r. Okay, so now if I look at my charge density, what I get is a charge density that is still dependent on r prime, t minus r over c plus r hat dotted into r prime over c. Okay. So now what we want to do is actually do a Taylor expansion of the charge density. So what we have is the charge density is equal to the charge density at r prime and what I would call t0 plus the derivative with respect to time of the charge density evaluated at t0 times r hat dot r prime over c, where rho dot is equal to, like I said, the time derivative of the charge density evaluated at the time t0. Okay. So what we're going to do is we're going to drop higher order terms. So we're just going to keep the first order, and we're going to neglect terms like 1/2 the second order derivative of the charge and terms like 1/3 factorial triple derivative of the charge density. So we'll drop those terms. We're just going to keep the first order derivative. Okay, so really saying that is our second approximation. What I'm essentially saying is that the position r prime is much, much smaller than c over second derivative divided by the first derivative. So yeah, and the same thing is true for like the third order derivative. So rho dot 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 divided by rho dot, sorry, 1/2 the square root of that. Anyway, so I'm saying that these higher order derivatives are much smaller than the first order derivatives. So we're going to ignore them. We're only going to stay with the first order derivative. Okay, so if we do that, then we can start to look at the integral. And so the integral of the electric potential is 1 over 4 pi epsilon naught, and I can take out an r. And I have now a couple of integrals. One is because I use the Taylor expansion, the first term in the Taylor expansion is just the charge density plus r hat over r dotted into the this is prime plus now the time derivative of the charge density Okay, so those are the terms in the Taylor expansion where I essentially have the last one is this one is related to rho dot, and the other ones are just the first order term. Okay, so now I have these three integrals to solve, and if I look at them, the first one, this one right here, is just a charge q at a given time t0. So it would be q at t0. The next one has a r prime integrated with the charge density, and so that would be a dipole moment, an electric dipole moment. Same is true of the third integral, but now I'm looking at the time derivative of the electric dipole moment. So let me write that out now. So our electric potential would now become 1 over 4 pi epsilon naught q over r plus r hat dotted into the dipole moment at a moment in time t0 divided by r squared plus r hat over rc dotted into the derivative of the dipole moment evaluated at some time t0. So we're now left with these three terms. Essentially the first one, which is the static, the first one, which looks like a Coulomb's law, and then the second one, which is the dipole moment, and the third one is a time-changing dipole moment. So let's only consider the static case. So this time derivative of the dipole moment we're going to set equal to 0. We don't want a time-changing dipole moment. And then what we get is an electric monopole of 1 over 4 pi epsilon naught q over r. And then we get an electric dipole, which is 1 over 4 pi epsilon naught r hat dotted into the dipole moment at some moment in time divided by r squared. Okay, so what we've essentially done now is to start with a time-dependent electric potential. So that's what we did. That's what we did differently than in previous chapters in the book. Is now we're considering the time dependence, and when we do that, what we end up with is our electric monopole and electric dipole, all evaluated at some particular moment in time t0. Now we did make certain approximations. The last one being that we aren't looking for time-changing dipole moments. So we're restricting ourselves there. In the general case, you could include one, but in this case, we're not. So what we're going to do in the next lecture, part 2, is to now consider the vector potential, A. And once we get the vector potential A, then we can take the electric potential, the magnetic potential, and find out what the electric field and the magnetic fields are for this kind of radiation.